Hi, welcome back, everyone. This is Chapter 5, Part 1, Variability. Now, I need to make sure that we're clear about this. This chapter is crucial. If you don't understand what we do in Part 1 and Part 2 of this chapter, especially Part 2, boy, you're going to be in trouble for most of the rest of the class. Make sure you understand what's going on in this chapter specifically. If you remember last time we talked about measures of central tendency. Central tendency has to do with, if you look at a histogram, right? If you look at the distribution of scores, what's in the middle? What's the mean, the median, and mode? That is central tendency, what's in the middle of a distribution. Variability has to do with how wide, how spread out the distribution is. That is variability. So the basic concepts we're going to talk about in part 1 today include the range of scores. That makes sense, right? So the lowest to the highest, that's the range, how spread out a distribution is. But we really want to focus on deviation and sum of squares. So deviation has to do with each individual person's score and how far away it is from the mean. And then the sum of squares we'll talk about in a little bit. We'll talk about what that means, or what that is in just a little bit. So first, let's talk about the deviations. If you'll notice that when we look at the deviations, this is the formula for the deviations, x minus the mean. Now, remember, mu, that's the symbol for the mean when we're talking about a population. And then for the sample, x minus x bar. X bar is the mean for the sample. These are the same calculation. We just call the mean something different when we're in a population than when we're in a sample. Okay? In the same way, sum of squares, we call this SS pop, sub pop, right? So this sub thing pop, that stands for the population. And then for the sample, we say SS, sum of squares, this SS. So the symbol is going to be SS sub pop for the population, or just SS, sum of squares. Now, the sum of squares is really crucial because there are a lot of different statistics that use the sum of squares as part of its formula, as part of its calculation. We'll talk about that in just a second. All right, so let's go ahead and look at some of the old data that we were looking at before. So we're going to go back. We're looking at the Menudo data. Well, don't look at that one. That one's coming up later. We're going to look at the Menudo data. Remember Menudo? We have all of the people in Menudo. So I've made this a little bit bigger. Hopefully people can see it. Right? So these are all of the different people who are in, who have been or ever were in Menudo, the boy band, right? Okay. And then this mean right here, this is mu, because it's for the population. This is everybody that's ever been in Menudo, and the population that I care about are all members of Menudo. All right. This is the mean tenure, how long they were in the band. So the average, the mean amount of time in years that they were in the band is 3.56. So the mean number of years that anyone in the entire population of Menudo was in Menudo is 3.56 years. Right? Okay. When we look at this, we need to look at the histogram. So this is all the stuff that we were messing with before, right? All the different things we were messing with before. I'm going to go ahead and erase a lot of this stuff because we don't need to talk about the skew right now. If you remember, the mean is 3.56, right? So that means that the mean is somewhere in between the 3 and the 4, 3.56, right about there. That's the mean. Okay? When we're talking about the range is exactly what you think it is. The range is the range of scores. So the lowest score is a 1. Actually, the lowest score was a 0. Does not include the 0. Let's go look back at their tenure data. Yeah, the lowest score. This is the tenure data, just the tenure data. Okay, the lowest score was a 0, and the highest score was 11. So that's the range, 0 to 11. Okay. Sometimes you minus it. You say 11 minus 0, that is the range. So the range is 11 years. So I don't really care very much that you know what that is in terms of like the actual number. I care that you know that here's 0 down here, right? And then here is 11 over here. So the range is the breadth. Okay, so the range is just the breadth of scores from top to bottom. That's all it is. Okay, fine. Now the mean is 3.56. We've talked about that. We need to talk about deviation because deviation is really an important concept. This is the mean in this distribution, 3.56. We're going to look at the raw data again. Okay, here are all the different scores. Now, a deviation is just for one person. So the most famous member of Menudo was Ricky Martin, right here, participant number 14. Ricky Martin was the most famous member of Menudo. And look, Ricky Martin had a tenure of 5 years. Okay? Ricky Martin had a tenure of 5 years. He was in the band for 5 years. So I'll move this over just a little bit. Ricky Martin was in for 5 years. You remember that the mean for everybody, let's go back down here, is 3.56. All right? So the deviation, when we talk about deviation, we're just talking about one person's deviation. So when I'm talking about the deviation score, I'm only talking about Ricky Martin's deviation from the mean. This is where this is really going. How strange is Ricky Martin in terms of tenure, in Menudo, right? We know that the average is 3.56. Well, is Ricky Martin different? Is he weird? Is he strange in terms of tenure? Well, we know that based off of we're going to start with his deviation. His deviation just says how much above or below the mean was his tenure. And so all that is x minus mu. Because we're talking about a population here, we're looking at x minus mu. X minus mu. So in this particular case, let's take a look. And we are going to make a new column right over here. I need to make it big enough so that you can see it. So let me change the size and stuff. So let's make this a big column, and we'll call it deviation. All right? We'll make this column called deviation. We're going to find Ricky Martin. Ricky Martin is this one. This is his last name. Ricky's Martin. Okay? And the deviation is going to be, remember, deviation is x minus mu. Come on, make my pen work. Mu, x minus mu for the population, or x minus x bar for a sample. It's the same thing, right? Mu and x bar are the same thing. It means the mean. Now in this particular case, we're going to do x minus mu because this is the whole population. It's really simple. It's the difference between this number, his tenure, versus the average. So it's going to equal his tenure minus the mean. X minus mu. That's what it's going to be. So Ricky Martin's deviation, I got to make this bigger for you. Ricky Martin's deviation is 1.44. That's it. It just means that he's 1.44 years greater than the mean. That's all it is. Deviation is not difficult, right? It's not very complicated. It is the deviation of the individual score away from the mean. Okay, now let's go ahead and erase these so that we have some space. And what we're going to do is let's go ahead, and I'm going to make sure that all of these, because what we're going to do is we're now going to get the deviation for everybody, not just for Ricky Martin, but for everybody. So I want to make sure that this is going to be 26 for everyone. Hopefully that stays the same. So starting with the first person, I'm going to get the deviation for everybody. So this is going to be I'm just going to make this bigger for us so that we can see it. The deviation of tenure. Now remember, this is the deviation of tenure that we're talking about. You would do a deviation for every variable. You can do a deviation for beginning age. You can do a deviation for end age. But we're just doing a deviation for tenure right now. Okay? So that's going to be the person's score, X, right? The person's score minus, and I'm going to make sure that this stays the same. So minus the mean, which is 3.56. Oh, I did it wrong. Equals this minus the mean. Okay? What I'm going to do right now in my Excel is I'm going to put some dollar signs in there. That says if I move this around, it's going to stay exactly the same place. I don't want the mean to move. All right? So this person's deviation, so this person is Nefti Sayaberi. Nefti Sayaberi has a deviation of negative 1.55 because the average is 3.56 and they have 2, right? So negative 1.56 is this person's deviation. We can get the deviation then for everyone. Everybody. This is the deviation for everybody. Let's go ahead and make sure that you can see these. So then, if you look, here are the deviations of everybody who's ever been in Menudo. You'll notice that anyone who has a score that's less than the mean has a negative deviation. Anyone who has a score that's above the mean has a positive deviation. And this deviation says, how different are you from the mean? That's what it's telling you exactly. All right, now I have a question for you. Let's go back to the slide. And here is the question. The sum of all the deviations in a sample, or in the population, doesn't matter. The sum of all the deviations is, the sum of all deviations is 0. The sum of all deviations is 0. What? 0? Why would it be 0? Well, think about it. Let's take a look at our data. Remember, everything that is below the mean, every person's score that's below the mean gets a negative, and everyone that has above the mean gets a positive. And those are always exactly away from the mean. So when you add them all up, they're going to add up to 0. They're going to add up to 0. So let me show you. I'm just going to do the sum. So this is going to be the sum of the deviations. The sum of all of these. The sum of all of these is, let's kind of expand this and I'll show you that it's 0. This is negative. All right, let's just tackle this right now so that we don't have to do it later on. Okay, this says 7.10. You're like, that's not 0. Okay, fine. See that E negative 1.5? So that E negative 1.5, you remember how this goes. That says that this means that we have a this is 15 places to the left of this decimal point, right? That there's zeros 15 places to the left, negative 15 places to the left. So that means that this number that you're looking at right here is, we'll count it out here. Ready? It's 0.0000000000000007. That's what we're looking at. The only reason why this doesn't say straight 0 is because of the rounding error 15 decimal places over. In fact, I think we might be able to move it over and find it. No, we can't because Excel doesn't even think that far. Yeah, it's only going to give you that many decimal places. That's 0. That's 0. The only reason why it's different is because these things are 15 decimal places over. Yeah, we should round that, really. Okay, this would be 0. That's 0. Well, okay, why do you care? The sum of all the deviations is 0. That's what you need to know. The sum of all deviations is 0. Well, why does that matter? Okay, remember, we wanted to know how different Ricky Martin is from the rest of the group. So here's Ricky Martin. Let's find him again. Here he is. This is Ricky Martin. His deviation score is 1.44. Well, how weird is that score? We know it's 1.44 years above the mean. We know that because that's what that deviation says. But how much do other people deviate from the mean? Nobody has a tenure of 3.56, which is the mean. So everybody's a little bit different from the mean. Wouldn't it be good to be able to find the average amount of deviation, the average amount that people deviate from the mean? And then we could say, well, the average amount of deviation from the mean is, 7. And so Ricky Martin's deviation of 1.44, that's not very weird. That's not very strange. The problem with finding the average or the mean deviation is that when you look for the mean deviation, you get 0 because a mean is the sum of everything divided by n. If we take this and then we divide it by n, so this divided by 34, which is the n, we get even a bigger 0. That's 0. The average of 0 is always 0. It's always going to be 0. So it doesn't make sense to create a deviation when we're talking about this. It doesn't make sense to do a mean deviation. It doesn't make sense to do it. And the reason why that doesn't make sense is because whenever you try and get that mean, you're going to get 0. You're going to get 0. So what do? Well, we need to talk about the sum of squares. We need to talk about the sum of squares. So let's go back to this, and we'll show you the sum of squares. Back to the slides. Come back. There it is. The deviation, you remember, was x minus the mean. So x minus mu for the population, x minus x bar for the sample. The sum of squares, we'll get to these in part 2, variance and standard deviation. That's coming up in part 2. The sum of squares is just the sum. Look, x minus mu. You see that? Look, x minus mu up there. X minus mu is the deviation. So we're going to take that deviation and we're going to square it. Remember PEMDAS, so exponent comes before sum. So the parentheses, do the stuff in the parentheses first. That's the deviation. Then we're going to square it. And then we're going to add those up. Now, why are we doing that? The reason why we are doing that is because when we add up the deviations, we get 0. But when we square things, remember when we square stuff, they're not going to be negatives anymore. So to get rid of this 0 problem, what we're going to do is we're going to take each of the deviations, we're going to square it, we're going to add those up. And that's going to let us get to something closer to a mean of deviations, which is really what we want to get to. We want to know how weird Ricky Martin is. We want to know if his deviation is different from other people's deviations. And so in order to do that, we can't just get the average, we've got to square it. We're going to start by squaring it and adding them up. So what do I mean by that? Let's go back to the data. So here's all of our stuff, remember, okay? This is the sum of all the deviations, which is 0, right? And these are all the deviation score. Ricky Martin's deviation was this one, just to remind you, he is right here. His deviation was 1.44. We want to know how strange his deviation is from everybody else's. Well, we can't do it by adding things up and getting the mean. That doesn't work. So we are going to instead take this deviation score, the deviation score for everybody, and we're going to square it. So this column right here is going to be the squared deviation. So this is going to be this squared. Okay? remember, x minus mu squared, and then we add them up, because the formula that we're working on is we want the sum of, in parentheses, x minus mu squared. X minus mu we already have, that's the deviation. Okay, this deviation is x minus mu. Now we're just going to square it for each one. So when I do that, 2.43, what I've got is everything except for that sum part. So x minus mu squared for this person is 2.43. Now we're going to do that for everybody. Okay, this is everybody's x minus mu squared. When we take the sum of that, when we take the sum of everybody's deviation squared, the sum of every deviation squared, we get 196.4. This is the sum of square. All right. This right here is the sum of square for the population. It is the sum of every deviation squared. So this column, the deviation, is x minus mu. We squared it, and then we added them up. Okay? That is the sum of square for the population. In the next video, we're going to talk about how you take that sum of square and what you do with it from there. Remember, the goal is going to be, how strange is Ricky Martin? That's going to be our goal. That's going to be the goal, trying to figure that out, okay? How strange is Ricky Martin is coming up. So this is for the population. We do the same thing for a sample, except that instead of using the mu symbol, we use an X bar. So let's go ahead and look at some of our old data, and we will ask you to do some calculations. So here we are. Remember, these are our data for cups of coffee, hours of sleep, and liking for donuts. We have the sums and the means, etc. So what I want you to do is I want you to calculate for me the range. So what is the range for liking for donuts? So specifically, I'm asking, what is the top score minus the bottom score? All right. So the top score is a 9. The bottom score is a 2. So 9 minus 2 is 7. The range for liking for donuts is 7. The lowest score is 2. Highest score is 9. That means the range of scores is from 2 to 9. That's 7 different places. Okay? All right. We don't care very much about that, but let's do a different one instead. What is the deviation for participant 1? What is the deviation for participant 1? All right, remember, this is how we're going to do deviations. I'm going to go ahead and make sure that this is big, and we're going to move things over so that you can see them. I'm going to actually freeze my panes in a way that you can see things without me being in the way. So let me do this. Okay. This should help us out so we can only work with liking for donuts. Back. All right. So we've got the mean there, right there. All right. We need to make sure this is big enough for us. So what we're doing is we're going to get the deviation. Okay? So the deviation for the first person, we're looking for, in this case, because it's a sample, this is going to be, hold on. The deviation is going to be, we want to get x minus x bar. Okay? So person 1, their deviation is going to be x, their score, their liking for donuts, minus x bar, which is the mean liking for donuts. So that person's deviation, participant 1's deviation, is negative 0.43. Negative 0.43. Negative 2.43. Sorry, negative 2.43. I don't know why I said that wrong. Negative 2.43. That's their deviation. What does that mean? Well, that means that a 3 is negative 2.43 liking units below the average, which is 5.43. Okay? Now, for deviations, let's get everybody's deviations. Oh, I didn't do something right. I need to move this. I need to make sure it stays in the same spot. There we go. When you pull something down like that on Excel, it'll not just take, it'll do it for this one, but it'll also change the mean unless you put those dollar signs in there. Okay? Great. So when we add up the sum of all these deviations, is 0, essentially. It's super close to 0. It's a rounding error by like negative 15 decimal places, right? So when we want to figure out how strange person number 1 is from being in the mean, then we can't really do it because we can't find the average. Well, we can't do it yet. All right, so what we need to do next is, what is person number 1's deviation squared? So what we're looking for here, instead of just the deviation, we want the deviation squared. Okay, so in order to find this, let's go ahead. I'll make this bigger as well. So that we can see it. This is going to be the deviation squared. Okay. So this person's deviation squared is 5.9. Just negative 2.4286 squared is 5.9. So let's go ahead and get everybody's deviation squared. Okay. When we do that, this is everybody's deviation squared. So what is the sum of squares? The sum of squares is just putting a sum on what we've already got. So we want the sum of all of these deviations squared. There it is, 49.7. We took all these deviations, we squared them, we added them up. We're going to use that a lot later on. Now you might have noticed when we went through these formulas really quickly, let me just show you the formulas one more time. The formulas of what we were looking at before. Come on, computer, don't freeze on me. We were looking at these formulas, and you saw that there was a different formula than the one we're looking at. Come back. There it is. I'm talking about this, the sum of x squared minus the sum of x squared over n. Whenever you are doing this, mathematically, you can just take each of the deviations, square them, and add them up. But mathematically, if you take the sum of the raw score, you square that. So you square all the raw scores, you sum them up. Then you take the sum of the raw scores, you square that, and then divide it by n. You're going to get the same thing. All right. So it's the sum of x squared minus the sum of x squared over n. So let me show you what that looks like, and then we can try and finish up here. So let's go ahead and go back to where we were. All right. So the way you do this one is you do this based off of the raw data, not the deviations. So I'm just going to insert some cells here, give us some space to show you what I mean. These are the raw scores, right? Liking for donuts, the raw scores, how much they like donuts originally. We want the sum of x squared minus the sum of x squared over n. So what we're looking for, let me just kind of remind you what the formula looks like. Let me get rid of those deviations. We'll move this over just one more so I can write in the formula. We are looking for the sum of squares, and you can do that in two different ways. You can do the sum of x minus x bar squared, which is what we did previously, right? That's what we did before. Or you can do the sum of x squared minus the sum of x squared over n. So that's what we're going to do right now. We're going to do that second formula right now. So in order to do this, you've got to square everything. So this is going to be x squared. So equals this squared. Okay. We're going to do that for everything. And we're going to get the sum. 256, this right here, that is this, the sum of x squared. Remember, PEMDAS, so when you see the sum of x squared, you got to square the x first and then sum it up. So this is 256, okay? This right here is 256. Then we need to figure out what is the sum of x squared. So the sum of x in parentheses squared, that's this sum squared, okay? All right, so we need to get that squared. Let's go ahead and I'll show you what that is. So this is this squared, 1,444. All right, so 256 minus 1,444 divided by n. What is n? N is 7. It's the number of people in our sample. So let's put a 7 right there. So what we need is this minus this divided by that. And that's what we're looking for. 256 minus 1,444 divided by 7. So let's go ahead and look at that. 1,444 divided by 7 is 206.28. So we want the sum of square. We want something. We want this minus that. 49.714. Look, 49.714 and 49.7, and if we expand this, you'll see it's 714. It's the same thing. The same thing. It's the same thing. Mathematically, it's exactly the same thing. Now, the only reason why we really go through this is because you're going to see this formula, the sum of x squared minus the sum of x squared over n. You're going to see that used in different formulas. You just need to know that that is the sum of squares. This is the sum of squares. All right, thanks, everybody.